Okay guys, so let's look at to this problem 7.31 page 342. Now we are given a B field as y squared x direction plus z squared y direction plus x squared z direction. So now we have to prove that, we have to show that the B field here is actually the magnetostatic field. So how do we prove? So based on our last lecture, we have learned, right, our fourth Maxwell equations in terms of integral set as here, close integral b dot ds equal to 0, or in terms of point form we have here divergence of b equal to 0. So you can use either one to prove that this B field actually is a magnetostatic field. So for simplicity, I will just to choose this method. So using the divergence of B equal to 0, so you can try. So if we say the answer is 0, so it shows that the B is actually magnetostatic field. So let's do it together. So based on our table of divergence, you can see from your textbook, a divergence of B is equal to dBx component over dx plus dby component over dy plus dbz component over dz. So from this B field equation, we know that, guys, this y squared is actually our bx component, and this z squared is actually our by component, and then this x squared is actually our bz component. So if you substitute all this value into this expression of divergence, you have here d over dx, and put here bx equal to y squared plus d over dy, and below here is z squared, and lastly our d over dz. Now our bz actually x squared, so which will result in 0 for sure, because all this actually just constant over their respective derivation. Okay, so now we proved already the B actually is a magnetostatic field. So now we are going to find the magnetic flux that pass through the certain surface given as the surface actually located at plane x equal to 1, and then the y given from 0 to 1, and also the z given from 1 to 4. So that's the surface of interest that we are given. So now we are going to find the magnetic flux. So based on the equation that we learned last time, the magnetic flux can be expressed B dot ds. So now we have B already as shown up here. So now we have to find the ds. So guys, so if you look at carefully from these conditions, we know that the surface now actually involve the y and z. So by right, guys, ds here actually only dy and dz, and for sure the surface actually here pointing in x directions, alright, because the s now remain constant. Okay, now so let's substitute all the value of v and also ds inside these equations. The B key given as above. So now we have y squared x direction plus z squared y direction plus x squared z directions, and now a dot the ds obtained earlier, now x directions, so the dy dz. Okay guys, so let's do dot product between all these components to the x over there. So now the x dot x, yes, we have a value, leave it there. Y dot x gonna have 0 value, and again z dot y gonna have 0 value, right? So let's substitute all the limit as well. So now for the y, we're going to have here y squared dy, and here we have dz, and the y from 0 to 1 and the z from 0 to 4. So finally we have here y cubed over 3 0 to 1 times the z now from 1 to 4, which will give you 1 Weber. Okay, 1 Weber only, because this is going to have 1 over 3 and times 3. Okay guys, so that's the idea how we can find the magnetic flux for this case. So now let's proceed to the third part. Now we are required to find the J, right? The J is actually a volume current density. So guys, if you can recall our last lecture, let's say we have a source of H, let's say a J, right? J is our source of H field, right? So for the J here, you can find the H field actually using either BSL or ACL. It means that we have a source and finding the field. So we can have these two approaches to be used. And now we are going to reverse the process. Now we have the H, but now we are going to find a J. So for this process, actually we are going to find the J from the H, which can be used our third Maxwell equations in terms of point form. What is it? So here, curl of H is equal to J. That's our third Maxwell equation to be used now. Okay, so we can find the J by applying the curl operations to the H based on these diagrams. So let's proceed to the next part. Now we already know that we can find the J by applying curl operation to the H field. So before that, we need to find the H first, right? The H can be obtained from the B as shown here, B over mu naught, and now we assume that it's free space environment. So the B here guys given as initially y squared over mu naught in x direction plus z squared over mu naught y direction plus x squared mu naught z directions. So all this actually is our H, which has unit of ampere per meter, right? So now we are going to find the J by applying the third Maxwell equations in terms of point form, given as here the curl of H is equal to J. So that's the idea. We have to find the J from the H, so just apply third Maxwell equations in terms of point form. So now, since you are dealing with Cartesian system coordinate, so you can just refer to your table of curl in your textbook. You can see, I think page 85, you can find the table of the Cartesian for the case of curl. So let's write together here. So you find here the curl of H the first one here we have d hz component over dy minus d hy component over dz now in x directions plus the next one here we have d hx component over dz minus d hz component over dx, and the whole term belongs to y directions. And then the third one here we have from your textbook d hy component over dx minus d hx component over dy. The whole term belongs to z directions. Alright guys, so based on this, our h equation obtained previously up there, so we know that guys, the whole term here is actually our hx component, and then the whole term here is actually our hy component, and then the whole term here guys is actually our hz component. So let's analyze one by one. If you can see from these expressions of curl of h, the first one here, dhz over dy, so this is our hz. So since there's no y term inside here, so here you're gonna have 0 value, because in hz there's no y term, so this one 0 value. Second one, hy over dz. Now this is our hy. Yes, we have dz, we have z term, so here you have value, leave it there. And then the third one, hx over dz. So this is our hx, which has no z variable, so now we get a 0 for sure. And then again the hz over dx, this is our hg. So yes, we have x common, so we have this value, leave it there first. And then the fifth one, hy over dx, and this is our hy, which has no x variable or x term, so we are going to have this one again 0. And then lastly, the sixth one, the hx differentiate over dy, so this is our hx. Yes, we have y, so we have this value for sure. So now let's proceed the differentiations of each components. So now we can have here the curl of h, here negative for the y right here, so d dz and hy here given as z squared mu naught x directions minus d dx, and this is your hz given as x squared over mu naught, and here we have y directions. And then lastly here, our d over dy for the hx component as shown here, which is y squared over mu naught, now belongs to the z directions. So if you proceed, you can have this final answer, negative 2z over mu naught x directions and negative 2x over mu naught y directions minus 2y over mu naught z directions. So okay, this whole term guys is actually refer to our J, which is our volume current density as required by the equations, and this one sure will have unit of ampere per meter squared. Alright guys, so I hope you can try yourself. So make sure you go through all the steps and make sure you understand one by one. Alright, so thank you and good luck for your study.